Magnetic field due to a toroidal solenoid. Very simple, students. The coil of this one represents the coil of wire will be wounded like a in a circular loop. In a bangle, you take a bangle, you wound a coil of wire over the bangle. That will be like this. So this center line represents the magnetic field. So this structure is called as a toroidal structure. So very simple, students. So this is a coil of wire. So the wire enters here. So it will be comes like this. So it will be wounded in the form of circular manner. So when the current passes through it, the magnetic field in the center of the coil, it is similar to the solenoid. So the center of the coil is uniform. That will be represented in the middle line. Okay. So this is a magnetic field. This is a coil of wire. The point in the open space interior of the solenoid. What is the magnetic field in the point P, open space interior of the solenoid? The radius from the point P to this circular loop, Amperean loop, is R1. So the Ampere loop radius is R1. The length of the loop is, what is the length of the loop? It is 2 pi R1. But that means the circumference of the loop. By Ampere circuital law, integral. The Ampere circuital law is integral B vector dot dl vector, which is equal to mu naught I. So for the B vector dot dl vector, we can write that BL, because this BL means the angle is theta is 0 degree. Directly we can write integral B vector dot dl vector is equal to BL. So BL, which is equal to mu naught I. So the current I is a uniform for a whole circuit. So the L1 is a Amperean loop L1. So B is equal to 2 pi R1, which is equal to mu naught. What is the current in the center? The current in the center of the loop is 0. So the magnetic field is 0. So inside the interior space, open space, the magnetic field of the toroidal solenoid is 0. Similar to the electric field is 0 inside the spherical shell. Point inside the toroid. So the Ampere loop is radius is R2. The length of the loop is L2 is equal to 2 pi R2. Very simple, students. If the point is inside the solenoid, that is S point, this point, then we are going to see that the third position, the point is outside the loop. If the point is at the center of the loop, the radius is R2. Here the radius is R3. So remember that. So for that second case, inside the toroid, the radius is R2 and the Amperean loop length is 2 pi R2. So Ampere circuital law, BL2, L2 means 2 pi R2 into mu naught Ni, because in the center there will be a current flowing, because the current is flowing in this loop. So this solenoidal loop. So we cannot take that as it is here the current is 0, because here the current is 0 because there is no coil of wire conducting a current in the point P. But in the point S, there is a coil having a current I passing through it. Hence, we can substitute that mu naught N is a number of turns, I is a current passing through it. So instead of this N, that is a total number of turns into the length L. So B into 2 pi R2 mu naught N I. N is a number of turns and L is a total length of the coil, that is 2 pi R2. That is that Amperean loop total length is a circumference of the loop. This one and this one will get cancelled. Finally we get the B is equal to mu naught Ni. Yes, the similar to the solenoid equation, here also we get the magnetic field is mu naught Ni. What happens to the point outside the open space? Very simple, students. As in the first case, the current is 0 in this case. So we get B is equal to 0. So I concluded that in a toroidal solenoid, the toroidal solenoid is similar to the normal solenoid, but the space interior to this solenoid is magnetic field is 0, and also in the outside is also 0. For both the cases, the current passing is 0. But in the center of the solenoid or in the interior inside the solenoid, the magnetic field value B is equal to mu naught Ni. Similar to the solenoid, B is equal to mu naught Ni. So this is also a derivation, but in the syllabus it is given that qualitative analysis, even though we are derive the expression for solenoid as well as the toroidal solenoid. Students, next we are going to see about force on a magnetic moving charge. Force on a moving charge in a magnetic field, not a rest charge, static charge. So this unit is a current, electricity and a magnetic effect of the current. So the moving charge, when a charge is moving on a magnetic field, what will be a force experienced by this charge? So that force is directly proportional to the magnetic field. That force is directly proportional to the magnitude of the charge. 1 coulomb of charge, 5 coulomb of charge. The force experience is different for 1 coulomb charge and 5 coulomb charge. Hence we can say that the magnitude of the charge. Then the force is directly proportional to the vertical component of the velocity, not a horizontal component, vertical component of the velocity v sin theta. Hence we concluded that this force is directly proportional, that proportionality constant is k b q v sin theta. Here we take k as a unity. Simply we can say that force on a moving charge in a magnetic field is directly proportional to magnitude of the field and the magnitude of the charge. Moving means velocity, the velocity component also coming. So F is equal to bqv sin theta. Hence this force is called as Lorentz force. This force will deflect, this force will applied on the charge, so this will deflect the charge. That force is called as a magnetic Lorentz force. In vector form, we can write that magnetic Lorentz force F is equal to Q into V vector cross B vector. So in this equation, B is a vector, V is a vector, Q is a scalar, it will be taken outside. So B vector, V vector, here it is a sin theta, that will be similar to A vector cross B vector, which is equal to AB sin theta. So it will be BV sin theta. So we can write that A vector cross B vector. So V vector cross B vector cross B vector. So that is a V vector cross B vector. So I will already say that what is the direction of this force. What is the direction of the force? Very simple, students. If the V vector and B vector is acting along this, I will explain with the cross product. If A vector and B vector are there, if you take the cross product, that cross product will be perpendicular to the plane of this paper. So if the cross product is along the plane of the paper, this cross product vector will be perpendicular to the plane of the paper. Similarly, the V vector is along the y direction and B vector is along the x direction. This V vector cross B vector will be along the perpendicular to the plane of the paper. So this is the direction of the force experienced by the charge. The charge force's direction is this direction. If the velocity of the charge is 0, that means if you take the charge is at rest in a external magnetic field. The question is the force on a moving charge in a magnetic field. If you assume that the charge is not moving, that is the charge is at rest, means what will happen? V is equal to 0 means BV sin theta, that is a BQV sin theta. Velocity is 0 means entire term will become 0. Hence the magnetic Lorentz force is 0. If you take that theta is equal to 0 degree or 180 degree, that means BQV sin 0 degree. Sin 0 degree means sin 0 1. So we get BQV. Then also sin 0 is a 0. We get the force is 0. Very simple, students. Then the magnetic field direction and the charge moving direction. This is a charge moving direction with velocity v. This is a magnetic field direction. If the both are in parallel or in the anti-parallel, if the charge is moving in the opposite direction with the magnetic field, so for both the cases 0 degree or 180 degree, the force will be 0. So when the force will be maximum means, because it is a cross product, sin theta will come. When the angle is 90 degree, the magnetic Lorentz force is maximum. Hence we come to the conclusion, the force on a moving charge, if the moving charge is moving along perpendicular to the magnetic field, if this is a magnetic field, if the charge is moving in this direction, the charge is moving in this direction, if the angle between them is 90 degree means the force is maximum. That is will be explained as F max, which is equal to QVB, magnetic Lorentz force. This force direction can be explained clearly by Fleming's left hand rule. Stretch your thumb finger, forefinger and middle finger mutually perpendicular to each other. If the forefinger represents the magnetic field, middle finger represents the current or the direction of the charge or opposite to the charge, the force will be in the thumb finger. So that's we can explain as a Fleming's left hand rule. So what is the magnetic field? We can define the magnetic field. This rule shows that Fleming's left hand rule shows the direction of the force. So the magnetic field, we can define the magnetic field with the help of the magnetic Lorentz force also. So F by QV sin theta. What is the SI unit of force? Newton. SI unit of charge is Coulomb and SI unit of the velocity is meter per second. So Coulomb per second is a current. So we mention as a ampere meter. This meter comes here. So Newton ampere per meter minus 1 is a 1 Tesla. So the SI unit of magnetic field is 1 Tesla. 1 Tesla is equal to Newton A power ampere power minus 1 meter power minus 1. So this is the SI unit of magnetic field. The dimensional formula is m t power minus 2 A power minus 1. Similarly, the Lorentz force can be classified into two things. That is electric Lorentz force and magnetic Lorentz force. Electric Lorentz force, already we have studied that F is equal to QE. So if we add these two things, we get a total Lorentz force. Total Lorentz force is Q can be both the side. We have a Q, so Q can be taken outside. E vector plus, we have to add both the things, V vector cross B vector. Hence we define that the total force experienced by a charged particle moving in a region of both electric and magnetic field. Electric field, apply the force on the charge. Magnetic field, apply the force on the charge. So the charge experiences both electric force and magnetic force. The electric force value is QE. The magnetic force value is Q into V vector cross B vector. That is QVB sin theta. So the total force experienced by the charge due to the electric field and the magnetic field is F is equal to Q into E vector plus V vector cross B vector. Dear students, in this session we are clearly studied about the toroidal solenoid. Then we are studied that the force on a moving charge in a magnetic field. What will happen if the magnetic field angles are changed? Velocity is 0, the angle is 0 degree and 180 degree, parallel and anti-parallel, and finally the angle is perpendicular. From this we can come to the conclusion that Fleming's left hand rule will be placed into the determining the force of the charged particle, force experienced by the direction of the charged particle. Then finally we calculate the total Lorentz force equation.